Thanks for the invitation. Let me say that again. Thank you, everybody, for being here today. Thank you for the invitation to speak. I'm honored to be able to present this to you. So my name is Chris Heunen. I'm at the University of Edinburgh, and I'd like to talk to you about some joint work that's been going on for maybe 3 years or something with these people from various other institutions. And what I'd like to talk about is called quantum computing from reversible classical computing. So the main idea is going to be quantum computing is this weird new phenomenon that's very cool, but it is a bit weird and we don't really know how to deal with it yet. But classical computing, of course, is something we know very well how to deal with. So there's a sub-part of classical computing, reversible classical computing, and I'll talk a bit more about this later, where all the computations you can run forward and backward, that we also know how to deal with very well. And then the idea is we're going to add a small number of things to that to a model of reversible classical computing to make it a model for quantum computing. That's the main idea. I'm not really sure of your backgrounds, and I'm not really sure if I'm tailoring it right for you to understand. But if there's anything at all you would like me to explain or go slower or anything tangential, please just let me know. I can't see your faces, so just unmute yourself and shout. Okay. So as I was saying, we're going to be thinking about quantum computing as a kind of completion. And I'm going to start with a quote by a famous quantum information theorist called Dorit Aharonov. And this is what she said about quantum computing. It's really something that is special for quantum computation because it's somehow complete. Quantum computing is some kind of completion, mathematically, of classical computation. I think of this as maybe similar to the fact that the complex numbers are an algebraic closure of the real numbers. So this was an interview. It was not a technical statement, but we're going to be making this statement very precise today. And as she's saying, she's thinking about if you start with the real numbers, not every equation has a solution. So you can sort of formally add all those solutions so that you can now solve all equations, and then you get the complex numbers. In the same kind of way, we're going to be starting with classical reversible computing. You can't solve all equations in there. You can't do everything you want in there. So we're going to formally add those solutions to get a larger model. And that larger model is going to turn out to be all of quantum computing. So that's the tone for today's talk. Let me say a bit more about this kind of algebraic closure, because I'm not sure how mathematically literate everybody is. Because sometimes when I teach undergrads, they know about matrices, but they mostly know about matrices of real numbers, whereas quantum computing is all about complex numbers, which sometimes they haven't seen yet. So a field, so that is a set of numbers in some sense that you can multiply and add and subtract and divide. A field is called algebraically closed when every polynomial has a root. So for example, here's the polynomial. I'm not sure which one I drew. It's something like x squared plus 1. Yeah, that's the one. That does not have a root, right? That does not touch the x-axis over here. So in this field, this equation does not have a solution. So it's not algebraically closed. If you go to other fields, for example, the complex numbers, the same equation, x squared plus 1, does have a root, namely the imaginary number I, because I squared is -1, so I squared plus 1 would be 0. That would have a root. It would touch the x-axis. So to find a solution to this equation, we need to do something to the real numbers to make them bigger, to sort of add these formal solutions, and we'll call this solution I, to get a new field that's larger, where all these things do have solutions. And that field will be algebraically closed. So there's a procedure you can do to any field at all to make it algebraically closed. And that's the kind of thing we're going to be doing. Now, later on in the talk, I'm going to be talking about universality. And I'm going to be talking about universality in two different ways. The first way is about computational universality. So that means in the classical sense of Alan Turing, for example, the Church-Turing thesis says that every function at all that you can think about, you can actually compute. Every computable function I can program on a Turing machine. So that kind of universality. Now, in a quantum setting, we have to be a bit more careful because, and we'll get into this later, a quantum computation consists of matrices over the complex numbers. So there's uncountably many such things, right? There's uncountably many complex numbers, and there's certainly uncountably many 2x2 or 4x4 matrices over the complex numbers. So there's very, very many of them. And we can only build countably many programs out of finitely many primitives. If your source code is finitely long and it can only use finitely many things like if, then, else, then of course you can only build countably many programs. So there is no way that any sort of countable programming language can ever be universal in the strict sense for uncountably many quantum computations. So when we say computational universality for quantum computation, we mean the following. For each quantum computation, for each unitary matrix that you can give me, and for each error margin epsilon, I can find a quantum circuit, so sort of one of these finite programs built from finite means, that approximates the target unitary up to error margin epsilon. So I can get as close as I want, as close as you want to any target you give me. So I can't maybe exactly build the function you're asking for, but I can get as close as I want. And we'll call that computational universality. And then there's a second kind of universality that I'm going to use, and this is called categorical universality. This is not so much about computation, but more about mathematical modeling of computation, of semantics of computation, if you like. And I'm going to take some time to explain this to you, because you've seen it probably before in various guises, but you may not have put a name on the property. The important thing about the property of categorical universality is that it can characterize a property up to isomorphism by looking how it behaves rather than actually how to build it. So a typical example you may have seen of this phenomenon, categorical universality, is the tensor product of vector spaces, and that's this picture over here. So if I have two vector spaces, V and W, let's say they're real vector spaces, doesn't really matter. I can think about bilinear functions going to a third vector space set, right? So these are functions that if I hold one argument fixed, let's say I pick a fixed vector in W, and I look at the function that takes an arbitrary vector in V to whatever that bilinear function does. If that function with this argument fixed is linear, and vice versa, if I fix this argument, the function is linear in the other variable. So such a function is called bilinear. And these things are not really nice in some sense because we can't talk about them with matrices, and matrices are great. So what you would like to do is somehow translate these bilinear functions into linear functions, because linear functions we can't talk about with matrices, and then life is much easier. So what the tensor product construction does is it builds a new vector space called V tensor W out of the old two vector spaces V and W that sort of classifies these bilinear functions. It sort of makes bilinear functions linear in this precise sense. So V tensor W, you can define it as it's some vector space that has a function from V times W into it with the following property. Whenever you have a bilinear function out of V times W, it must factor through a linear function out of V tensor W. So any bilinear function out of the product is the same thing as a linear function out of the tensor product. And that's a very easy property, right? It says exactly what you want the tensor product to do. You're saying, you're just sort of giving a specification of, I want this tensor product to make bilinear things linear. And this is called a universal property, and it typically has a form for every something something, for every function out of a given object, there exists a unique other function out of some other object such that, this triangle commutes. Doing this and then that is the same as doing that. So this is a specification. You still have to prove that such a thing exists. And you have to get your hands dirty and actually build one. Often you can do that with generic means as well. But once you've done that, there's no choice, right? This property, this categorical universality fixes what this space has to be up to isomorphism. So anything you can come up with that satisfies this specification has to be this one up to a bijection. So that's what I mean when I say you can characterize something by a behavior rather than by actually building it. Here I have another example of this phenomenon, just to get you used to the idea. This is about, in type theory, about exponential types, about function types. And it says the following. Whenever you have three types, x, y, and z, sorry, we have two types, z and y. And I would like to think about something like the type of functions from y to z, and we'll write this as z to the power y. What does it mean to be a function type? Well, one thing you might write down is I will call z to the y a function type when it has something like an evaluate map, like this. I take a function, I take an argument, I can evaluate it to get an output. Well, that stands to reason, I think. But then this z to the y object might be either too small or too big. So we can, again, put some sort of universal property on it to make it sort of just the right size. And this time, universal property says, if there's any other thing you might think of as something like a function type, x, some sort of pretender exponential object, some sort of pretender function type, then there exists a unique map to the actual function type that makes this diagram commute. So that if you give me any of these fake functions and any argument and any way of sort of evaluating the fake functions on the arguments, then you must actually go through the actual function types. So in some sense, this is the smallest type that has an evaluate map like that. And again, this is a kind of universal property because it says something like, for every such thing, there's a unique such thing that makes the triangle commute. And again, this specifies what this function type looks like up to isomorphism, up to bijection, sort of nails down what it needs to be for this behavior to occur. And that's what we'll call categorical universality. And this is going to be an important property for us. Okay, so there's two kinds of universality. Don't get them mixed up. One says every quantum function I can approximate with circuits. The other says I can characterize properties by their behavior rather than building them. So what we're going to be trying to do is start with classical reversible computing, put some of these properties on by behavior. I'm going to specify I want this and this kind of behavior. And that sort of fixes the model in the second sense of universality. And then we're going to be proving that it is universal in the first sense. Okay, next, I have to tell you a bit about category theory, because the models we're going to be building are going to be categorical models. And you can think about the kinds of categories we're talking about as something like fancy versions of the natural numbers. So just the numbers 0, 1, 2, 3, 4, etc. A fancy version, I mean, think about finite sets. So of course, every finite set has a cardinality, which is a natural number. But not just the sets as objects, but also the functions between them. So that's sometimes called a categorification, because we're not just talking about the objects, we're talking about the relations from the objects to each other. So think about finite sets and functions. This is what's called a category. Because you can do several things. If I have a function f going from some finite set A to a finite set B, and I have another function g going from B to C, then I can compose the two functions, right? I can take an input in A, feed it to f to get something in B, and I can feed that thing as an input to G and get an output in C. So for every f and every g, there exists another function that we'll call g after f, g composed with f, or sometimes even g times f, that goes from A to C. And similarly, there's something like a function that does nothing, right? It takes an input in A, some element of A, and returns that very element. So it's the identity function. And these two things together are the data of what's called a category. So finite sets and functions, first of all, form a category. This data has to satisfy some things for these composition and this identity to make sense. And it's sort of the obvious things that you would expect. Namely associativity. If I have three functions going from A to B and from B to C and from C to D, then I can first compose the first two like this and then compose on the third. Or I could put the brackets the other way and first compose numbers 2 and 3 and then compose number 1. Either way, I'm going to get a map from A to D, and I want these two maps to be the actual same function. Of course, for functions between sets, this is completely true. And similarly, I say that this is a function that does nothing, that takes an input to itself as an output. But I mean, there has to be some sort of axiom that actually forces this. And the axiom says this: if I have any function f whatsoever, I post-compose it with an identity that does nothing. Or if I pre-compose it with an identity that does nothing. So that's this identity law over here. So this data, a bunch of objects, a bunch of maps between them, a way to compose an identity maps satisfying these two laws, that's what's called a category. And again, just think about finite sets and functions. Now, sometimes it's handy to draw these kinds of things graphically. So we can think about the objects, the finite sets, as wires like this, and the functions as boxes turning an A wire into a B wire. And then you can think about composition over here as just stacking the boxes on top of each other, first doing F, if time goes up, first doing F, and then doing G. Right? And then an identity wire, an identity morphism like this, is like a box, like an empty box, just a wire that does nothing. And then these two maps, sorry, these two axioms are completely trivial. They just say, it doesn't matter which order I draw my picture in, I get the same picture. Okay, so the first column here is just telling you what it means to be a category. But finite sets and functions, like these fancy versions of natural numbers, you can do more with natural numbers than just state them as, as elements. What you can do to natural numbers is you can multiply them and you can add them. And similarly, you can do a fancy version of that for finite sets and functions. So the middle column here is going to talk about multiplication first. And this is what's called a monoidal category, or sometimes a tensor category. And it says that, again, I have to have some construction available. It has to satisfy some laws. And again, you can draw some sort of pictures to go with that. So let's go over that slowly. How do you multiply in this fancy categorical way? If I have a map from A to B, let's call it F, and I have another map from A prime to B prime, let's call it F prime, I want to be able to do two things. First of all, I want to take the objects A and A prime, and I want to build a new object out of them. So if A was a finite set and A prime was a finite set, I could take their Cartesian product, for example. Right? This is a new set. I can do the same to B and B prime and get a new object, this Cartesian product B times B prime, B tensor B prime. And the second thing that this rule is saying is if I have functions from A to B and F prime from A prime to B prime, I want to be able to put them together like that, to go from the product of the A's to the product of the B's. So if these are finite sets, you know how to do this, right? You can take the Cartesian product of the functions. So now this thing takes an input, as input, a pair of an element of A and an element of A prime. You can just apply the F to the element of A and the F prime to the element of A prime. So that will give you as output an element of B and an element of B prime. And that pair, is the output for the product function. So that's what it means to be a monoidal category, to be able to do this, to put objects together in a sort of parallel way and to put morphisms together in a kind of parallel way. And again, this has to satisfy some axioms. And it's very similar to what we had before. This putting together objects and maps has to be associative in the sense that if I have three of them and I put them together, it shouldn't matter where I put the brackets. Similarly, there's an object that sort of does nothing. If I put it together with any object A, I get the same object. So if we're thinking about sets and finite sets and functions, if A is some finite set, if I take the Cartesian product with a singleton set, of course, I'm going to get a set that's isomorphic to the original. So even simpler, if I have a natural number A and I multiply it with 1, I get the same number. Multiplying with 1 doesn't do anything. A third thing I'm going to ask is that A times B is the same as B times A. Right? If I put A and B together as finite sets, the Cartesian product of them is going to be isomorphic to the product of B times A. This is not always the case. So this is what's called a symmetric monoidal category. One subtlety that I'm brushing under the rug here is that here we had equations, literal equations. This morphism, where I put three functions together, is literally equal to that other function. But here, these objects are only isomorphic, because if I take the set, the Cartesian product of some set A with a singleton, is not literally the same set as the one we started with, right? There's a bijection between them, but it's not actually equal. So there's some subtleties there. But it's nothing we need to worry about for this talk. Okay, so first column was category. Second column is what's called symmetric monodal category. And now the graphical calculus gets a bit more interesting. So in a category, we can have these boxes for the processes, for the maps, for the morphisms that we can stack on top of each other. In a monoidal category, we can also put boxes next to each other. So we can draw, in this case, f tends to f prime, as I have a box for f, and then just next to it, I put a box for f prime. And then this symmetry condition over here, that a times b is the same as b times a, looks like this in a picture. If I have two objects, a and b, I do f to the one, I do g to the other, and then I swap them around. That should be the same as first swapping them around, and then the order of the two is switched, so I should apply f to the second one and g to the first one. And you can imagine you can draw larger diagrams like this, and it makes computations easier. All right, so we have something like natural numbers. We can compose them. We have something like multiplication. The last thing you can do with natural numbers is add them. So finite sets and functions are not just a category, and not just a symmetric monoidal category. They're symmetric monodal category in two ways. Because if I take two sets, if I take two natural numbers a and a prime, I can also add them to get a third natural number, a plus a prime. And the same goes for a finite set. If a is a finite set, a prime is a finite set, then I can take the disjoint union of a and a prime. That will give me a new set, a o plus a prime. That's still finite and sort of has the right cardinality. And if I have a function from a to b and a function from a prime to b prime, I can take the disjoint union of the a sets and the b sets, and I can sort of act with one function on the a part of the disjoint union to get to the b part of the output, and with the f prime to the a prime part to get to the output part. So I can put sets together by disjoint union, and I can put functions of the right type together in a disjoint union. So finite sets and functions is a symmetric monodal category in two ways. I can take Cartesian product, I can multiply natural numbers, or I can take disjoint union, like add two natural numbers. And the final thing about natural numbers is that multiplication and addition work together in a certain way, namely in this way, that multiplication distributes over addition. So if I have natural numbers a, b, c, then if I first add b and c and then multiply the result with a, that's the same as first multiplying a and b, and then adding to that the multiplication of a and c. Right? So you can take the multiplication sort of inside the brackets, if you like. That's the binary version. The nullary version of that is a times 0 is 0 for any number a. So that was for natural numbers. The same kind of thing holds for finite sets. So the Cartesian product of a finite set A with the empty set is just going to be the empty set. And similarly, Cartesian product distributes over disjoint union in exactly this way. So these are the kinds of models that we're going to be thinking about. These things are called rig categories. Rig is short for ring without negatives, so ring without the letter n. And a ring is something like the natural numbers, which is a bunch of elements where you can add and multiply, and multiplication distributes over addition like this. So just think about finite sets and functions, if you like. That's going to be the kind of model we're interested in. Okay, so that's all the preliminaries. Now I'm going to talk about first reversible classical computing, and then quantum computing in 2 steps. So let's start with reversible classical computing.
Oh, I have a really simple question.
Yeah,
is there
shoot.
is there any diagram for like representing the third type of category?
Sorry, representing the third type of what?
Yeah, the third type of categories. I mean, you draw these 2 diagrams for like first and second.
There exist these kinds of diagrams. So this is like a one-dimensional graphical calculus.
Mm-hmm.
This you might think is 2-dimensional, but it's actually 3. There's these things. This goes over and under, right? And
okay.
In some sense, F and G go on top of each other.
Yeah.
So there's a 4-dimensional graphical calculus for this that has like sheets, where in each sheet you have a diagram like that, and then they can cross over in funny ways. So it's very hard to draw.
I see.
It does exist, yes.
Okay, thank you.
Any other questions? Again, please interrupt. All right, so reversible classical computing. I'm going to explain this by way of analogy. And this is actually a very good analogy because it was invented by two of the founders of the field, Fredkin and Toffoli, in 1982. And we're going to be thinking about billiard balls. So imagine this green thing here is a billiard ball, and you have a very funny shaped table like that with 1, 2, 3, 4, 5 pockets. We're going to think about 2 of the pockets as input ports and 3 of the pockets as output ports. So we're going to be thinking of these 2 as the input, like a bit, if you like. If the bit is 0, I'm going to be putting a billiard ball into here. If the bit is 1, I'm going to be putting a billiard ball into here. And the output, I'm going to think about these as the output. If a ball comes out here, I say the output of the function is 0. If the output comes out here, I say the output of the output bit is 1. So of course, this table, nothing interesting happens, right? If I put a ball into here, it goes straight ahead, nothing happens, it comes out there. So this is like the identity function. If the input is 0, that means I put a ball in here and I shoot it on its way, it goes straight ahead, it goes out here, so the output is 0. But what happens if I put a ball in both? Right, so I put a ball into the 1 pocket, I put a ball into the 0 pocket. Now the balls collide over here, so this one hits that one, and we're assuming there's no friction and everything is perfect. So this ball that came in here will get bounced off in that direction. The ball that came in here will get bounced off in that direction. Now the shape of the table was a bit funny because it had these cut-off angles over here. So the ball that goes down here bounces on the wall, goes that way. And same way on this angle, the ball that came in here, bounced off there, is now going to bounce off this wall straight down. And these 2 balls are going to hit each other again over here. So the ball that came down now is going to be reflected that way. And the ball that came here is going to be reflected towards this output port. So what happened is if I put in a single ball, either in 0 or in 1, nothing happens, right? I get 0 or 1 as the output is equal to the input. If I put in no balls, of course, nothing happens and no balls come out. If I put in 2 balls at the same time, I get a ball in the 1 output port, but I don't get anything in the 0 output port. I get it in this extra output port. So what you can think about is that this billiard table, in some sense, is an implementation, a physical implementation of a function that computes the AND, the conjunction of the 2 inputs, in the sense that a ball will come out here if and only if both of the input bits were set. Right? If I put bits into both the 0 balls into both the 0 and the 1 pockets. If we write out the table like the truth table for this function that we're computing that way, so 0, 0 is like putting no balls in, no balls come out, so the output is 0. 0, 1 would be I put 1 ball in, and 0, 1 comes out, etc. But if I put in 1, 1, then you get an AND out there. This bit is only set when both balls go in. So that's a small example of a billiard ball computation. And the point of this is that twofold. One, this is a physical model for computation. I mean, these billiard balls are physical things. We can use nature to compute this AND function for us. And 2, this model is universal. If you had enough billiard balls and a large enough room, you could build any Boolean function whatsoever out of billiard balls like this. So let me stress that again. This is universal in the sense that if you have an infinite supply of billiard balls and an infinite field in which you can build billiard tables with funny angles, you can build any Boolean circuit like this, any function from bits to bits. So that's the idea. Oh, sorry. The third point is, of course, this thing is reversible because I was talking about these as the input ports and those as the output ports. But I can also put in a ball in the output port and shoot it straight ahead, and we'll come back to the input port. And this whole thing about the balls colliding, we can run that backwards as well. If I put in a ball here and I put in a ball there, they will collide there, they will shoot up in that way, and then we'll shoot up in that way, collide here and go that way. So you can sort of, if you were to take a movie of how the balls move, you can play the movie back in reverse, and it will still satisfy the laws of nature. Right? So this is a reversible computation that is universal in the sense that you can build any reversible computation like this. So that's the idea behind classical reversible computation. Very excited about this for a while because it's more energy efficient. If you can make a classical computation reversible, that means you do not ever have to destroy or introduce new information. So in the sort of sense of thermodynamics, that means you do not have to do work. So if you can build a processor based on these sort of principles, that would not expand heat. And in that sense, it would be much more power efficient and doesn't need any sort of ventilation. It would be faster. And actually, some of this is used in practice. So that's the idea of classical reversible computations. So I was saying that these kinds of implementations are universal for reversible Boolean functions. Right? So if you forget about bits for a minute, a Boolean function we can think about as a matrix of zeros and ones. So it's saying, this input, if the columns are indexed by inputs and the rows are indexed by possible outputs, then such a matrix is saying that the third input is going to go to the first output and no others. So this is a reversible matrix in the sense that it's an invertible matrix. In this case, about 4 rows and 4 columns, so a set with 4 elements. It would be this permutation. Right? So the first column is orange, the second column is green, the third column is blue, the fourth column is red. As I was saying, the third element, in this case the blue input, gets sent to the first element, so it goes to the orange output. And you can make a picture of this whole matrix like such. So orange goes to blue, blue goes to orange, green goes to red, and red goes to green. And any permutation, I can make a matrix with entry 0 and 1 that is invertible. And any invertible matrix with only zeros and ones, I can draw as a permutation like that. And as we saw, as I've been arguing, permutations give semantics for reversible classical programs. If you have some sort of set of states, in this case, there's 4 states, and some sort of computation that evolves these states into, some other version of these 4 states, any function, I can run that function forward and backward. It's reversible exactly when the function is a permutation, when it's a bijection. So for reversible classical computation, we're interested in semantics, for example, in finite sets and bijections. Now, some permutations, so the one we drew here, that sort of swaps the leftmost 2 things with the rightmost 2 things, happen to be a composition of 2 other permutations like this, right? The same permutation and then the same permutation again. So I could send orange to green, and green to blue, and blue to red, and red to orange. So some sort of, cyclic shift to the right. And if I do that twice, then orange gets shifted once, gets shifted twice, ends up where we wanted it. Same, green gets shifted once, gets shifted twice, ends up where we want. Blue gets shifted once, then twice in a cyclic way, ends up where we want. So if you look at this, it's saying that this permutation over here has a square root. For this permutation, there exists another permutation, so that if I do that other permutation twice, I get the one that we started with. So some permutations have square roots. And so now we're starting to go back to where I started with algebraic closure of fields, and not all polynomials have solutions. Sorry, some polynomials have solutions in some fields, but not all polynomials have all solutions in all fields. It's the same kind of thing for these permutations. So this permutation happens to have a square root. So in some sense has a solution for the polynomial x squared plus this f. But how about this permutation? If I take a set with 2 elements and I swap the 2 elements, There is no way you can ever write that as a composition of some permutation with itself. So this permutation does not have a square root. Right? So this model of finite sets and permutations is not complete in the sense that not all polynomials have solutions. So in that sense, classical reversible computing is not complete. Okay, so I've been talking about billiard balls and about colored dots with permutations between them. But as proper computer scientists, you want to make this a bit more precise. So you can make this into a programming language. So you can make a programming language for these kinds of permutations. This programming language on the right here is called Pi, like the Greek letter for P for permutations. It's a combinator language in the sense that you have it's typed. So you have some types and you have some terms of those types and some rules for how you can make new terms and types out of old ones. So let me not go through all of them, but maybe point out some of them. There's something like basic types like 0 and 1 that you can add and you can multiply. So something like all natural numbers you can write as a type. And then you have types like function types like this that you can think about as permutations between a B element set and a B element set. So the kind of function you can think about is the permutation that does nothing, the permutation that goes from B plus C to C, it's over here somewhere, this one, B1 plus B2 to B2 plus B1, that just sort of swaps two elements. So that's something like this. The swap for 2 plus 2 into 2 plus 2 would be that kind of function. So we can just put a primitive element in our programming language. We'll call that swap for plus. Similarly, there's a swap for times that does the same thing for the times multiplication type. And there's various types for these kinds of things that we had a couple of slides ago about, it doesn't matter where you put the brackets if you multiply three numbers. Same kind of thing here. If I have three types, B1, B2, B3, I can make a new type out of that by putting the brackets this way, or I can put the brackets the other way. I want it to be a term, like a permutation, if you like, that turns one into the other. Going from left to right, I'll call it associate R. Going from right to left, I'll call it associate L. And that way we have all these sort of basic pieces of code in our programming language that we can use to build larger programs from. And you can build larger programs exactly in the way that I was advocating before with rig categories. You can first do one and then the other, so compose them in series. Or you can compose them in parallel, either with plus or with times. And then this one I want to point out, this basic function called dist, or factor, if you read it the other way, will make you able in the programming language to say that B3 multiplying with B3 distributes over addition. So the same kind of thing we had on this slide, that multiplication distributes over addition, has a counterpart in the programming language and is called factor or dist. We're going to insist that these combinators, behave in the programming language like we thought they should. Like if you have a permutation that goes from B1 to B2 and one from B2 to B3, then you can compose them like that. And the same for combining things with plus and with times. And that's the whole programming language. So it's very, very basic. It's a sort of assembly language, if you like, for programming with permutations. But you can build quite cool stuff this way. For example, you can build, if you have any permutation, I can make a controlled version of that permutation. So if that permutation, let's say, goes from n bits to n bits, then this is a new permutation that goes from n plus 1 bits to n plus 1 bits. And it sort of looks at the first bit. If the first bit is 0, it does nothing to the rest. If the first bit is 1, it will do the old permutation to the rest. And you can write that out in this language like this, where a bit I'm thinking about as 1 plus 1, right? Like a two-element set. Another interesting thing you can build is if you think about a bit as, 2 is 1 plus 1, then I can take the swap of, here's 1 plus 1, a 2-element set. Here's another 1 plus 1, 2-element set. There's a permutation between these that swaps the two, right? That was one of the basic things we're allowed to write in a programming language. I can call that gate X. So something like a NOT gate. If you think about this as a bit, then what it does, if you think about this as 0 and this about 1, then what this gate does is it turns 0 into 1 and 1 into 0. So it's like the NOT gate, the negation gate. And then you can start putting these things together. You can have controlled X, for example, which is something that looks like that. And you can build controlled X. So this will perform a NOT on the third bit only when the first two bits are set. So this is sometimes called a Toffoli gate. And the nice thing about this Toffoli gate is that any reversible permutation between bit strings, you can always write as a circuit of Toffoli gates. So once we build this one, we know that any permutation whatsoever, we can write down in this language. So this language is universal for classical reversible computing. There's some other nice things about this language. I've told you it's strongly typed. It has semantics and rig groupoids. That means that whenever you have a rig groupoid like this, for example, finite sets and functions, and whenever you have a piece of code in this language, I can interpret the code in that model in a way that preserves all the structure. So I can prove things about programs in this language in any of those rig categories as a model. So the one example I've been talking about all the time is finite sets and permutations. They form a rig category. They in fact form what's called the initial rig category, in the sense that if you give me any other rig category, there's a copy of finite sets and permutations inside that other rig category. I've told you about this, right? The Toffoli gate means that this programming language is universal. Another way of saying that is any permutation between finite sets. You give me a finite permutation between sets. I can always find a program in this language whose interpretation in finite sets and functions is the permutation you gave me. So this is great, it's universal, it's sound, this programming language, it has good semantics. And it's even better because this language is equationally fully abstract. That means that whenever you have two pieces of code, F and G, that we think about as permutations, they're going to be equal as pieces of code. I can prove that they're equal using these combinators. So just by a finite step of, a finite derivation of combinators. So the two pieces of code are equal if and only if their interpretations are equal in any rig groupoid. So that means I can prove stuff about these programs by purely equational means. Right? Two programs are equal if and only if I can find a finite set of rewrites of the programs where they locally only change according to these rules. So there's a very small finite number of equations that you can build, that you can use to change one program into another. Okay, so this language is called Pi, and we can use it to program with permutations. Next, we're going to move away from reversible classical computing, and we're going to start talking about quantum computing. I'm going to do this in 2 steps, because that's the way quantum computing works. There's a sort of reversible part to it, where it's no longer bits, but quantum bits, and you do some reversible gates to them. And then at the end of the day, you make some sort of measurement. You read out, if you like, the output of the quantum computation. So we're going to be first talking about reversible circuits, like the reversible part of quantum computation, and then later on talk about measurement, which is sort of the irreversible part. And the idea is that for both, we're going to give a universal property that if we add it on top of this language Pi, it's going to be universal for, in this case, reversible quantum circuits. So first I have to tell you a bit about how quantum computation works in the first place. So before we had, when we talk about reversible classical computing, we had, where did it go? Matrices like this, right? If we're talking about functions from 4 to 4, they would 4 by 4 matrices with entries in the Booleans and zeros and ones. quantum computation is a bit different in that if you still have n by n matrices, but now the entries are no longer Booleans, they're going to be complex numbers. And they're not just going to be invertible matrices with complex entries. They're going to be what's called unitary matrices, which means this sort of thing. It's not just invertible as a matrix, but it's in fact invertible by its own complex conjugate transpose. So if you give me an n by n matrix F, I can sort of flip it around the diagonal. I can transpose it, and then I can conjugate every entry, complex conjugate every entry. So that's called F dagger if you do that. So a unitary matrix is a matrix F, such that if I do first F and then F dagger, that's the same as doing nothing. And also if I do first F dagger and then F, that's the same as doing nothing. So in other words, the inverse of F is invertible and the inverse of F is F dagger. And these are the basic building blocks for evolution of quantum systems. So now we're no longer talking about 4-element sets, but about 4-dimensional vector spaces, for example. And they don't evolve according to this matrix of zeros and ones. They evolve according to a matrix with complex entries. And just like classical reversible computing had semantics in finite sets and permutations, reversible quantum computation has semantics in finite vector spaces and these kinds of matrices, unitary matrices. Okay, that's the basic setup. Now, these unitaries are a bit like complex numbers in the sense that I can make polynomials with these unitaries. If you give me a bunch of unitaries, I can add them, I can multiply them, and I can take powers of them. And it turns out, if you look at a polynomial of the form x squared plus f, that always has a solution. So in other words, every unitary matrix has a unitary square root. I can always take square roots. And the way you could do that, if you remember your linear algebra, is you can diagonalize your unitary matrix. So on some basis of the vector space, you can write it as a matrix with all zeros except on the diagonal. And you can take square roots of each of the numbers on the diagonal. Right? These are complex numbers. They all have a square root. And then you can sort of undiagonalize again. So that's an important property of unitary matrices. Every unitary has a square root. This was not the case, if you remember, for Boolean matrices like that, because this one did not have a square root. So somehow unitary matrices are a much larger world in which square roots do exist. So now you can wonder, as I was saying, not all reversible classical programs have square roots, and all quantum programs do. So you can wonder, can we think about reversible quantum computing as a closure in the algebraic sense of adding solutions to polynomials of reversible classical programs? And of course, the way I set up the talk is the answer is going to be yes. I'm going to tell you how. But so that's the main idea. We're going to start with this programming language Pi, classical reversible computing. We're going to add square roots, and then we're going to get all of quantum computing like that. So here's the few square roots I'm going to add. And we're going to get slightly more technical from now on. So we're going to take our programming language Pi that we had just for computing with bits. And I'm going to add two new primitive constructs to this. One we'll call W, or omega, which goes from 1 to 1. So we're thinking about this as a one-dimensional vector space now, something like the complex numbers itself. So this thing is a bit like a number, right? A scalar. And I'm going to add a 1-qubit gate. So this is a 2-dimensional vector space. Before we were thinking about it as a bit, now it's going to be a qubit, a quantum bit. And this V is going to go from 1 qubit to another qubit. It's going to be a gate that takes one input qubit and produces one output qubit. I'm going to add these two things. Formally, I'm just going to add them. These are now legal pieces of code. And I'm going to insist that these two new generators satisfy 3 equations, and 3 equations only. I'm going to ask that V is a square root of swap. So if you remember, the swap is something that goes from 1 plus 1 to 1 plus 1 and sort of swaps the two 0 and 1. If I take V and then V again, I want that to equal swap. So in other words, V is a square root of the NOT gate. Right? This thing that we didn't have before, this permutation, the NOT gate did not have a square root in finite sets and permutations. It does have a square root in unitaries, and I'm just going to formally add such a square root of a NOT gate to our programming language. That's the first equation. Second equation says that W, this number that goes from a one-dimensional space to a one-dimensional space, is really just multiplication with some number. That's a square root of a square root of a square root of the number 1. So an 8th root of unity. The third equation looks a bit mysterious, and we'll, if we have time, we can go into it a bit more later. It says that VSV equal SVS, where S is a certain thing built out of W. So it says some sort of cooperation between V and W. The picture over here tries to illustrate this third equation, VSV equal SVS, on what's called a Bloch sphere. So before 1 plus 1 was a bit, because it was a 2-element set. Now 1 plus 1 is a 2-dimensional vector space. And you can think about that, a 2-dimensional complex vector space. You can think about that as a 3-dimensional sphere, real sphere. So you can draw this kind of picture, and things on the surface of the sphere are states of a qubit. So if I start with a qubit over here, for example, there is 0, the north pole is 0, the south pole is 1. What happens if I do VSV to it? We sort of do V and then, where are we going? V and then S and then V, you end up over here. If you do SVS, you traverse a different path over the surface of the sphere, but you end up at the same point on the surface. So in that kind of sense, you can see geometrically that this equation is valid. It still may be a bit magic where it comes from, but we're just going to impose this thing. So to summarize, we're going to take our old programming language for permutations. I'm going to add 3 things: a square root of NOT, an 8th root of the number 1, and I'm going to insist that they satisfy this magic equation. And that's all we're going to do. That's the magic part. So that was the syntax, if you like. That's what our programming language now looks like. You can say things like swap plus, you can say things like V, and you can put them together with plus and times and composition. On the semantic part, models are not just going to be rig categories as before, so things where you can compose and add and multiply. We need to have some special maps in there that we can use to interpret these 2 new things, W and V. So I'm just going to ask that my rig groupoid has 2 special maps, omega and V, of the right type, satisfying the 3 equations. Because these 3 equations are something that makes sense in any rig category. I can just ask that my model satisfy it. Now the point is that we saw a bit already with these 2 Bloch sphere, is that if I take not finite sets and permutations, but I take finite dimensional vector spaces and unitary matrices, so that's the semantics for quantum computation, they form a model of this programming language, because I can interpret this new number omega that we need to be literally an 8th root of unity, the complex number that's such that if I take its 8th power, I get 1. And for this extra generator V, I can take the 2x2 unitary matrix that looks like that. And this happens to be one of the standard gates in many quantum computing platforms. So if you take unitary matrices, if you take omega to be this, you take V to be that. Of course, you still have all permutation matrices in there, because permutation matrices are unitary. You have these 2 extra things. They will satisfy these equations. So there's at least one model for this programming language, which consists of unitary matrices. Now I'm going to have to talk a bit about quantum circuits. So just like in a Boolean circuit, you have a standard set of gates, like OR and NOT and these kinds of things, and TOEFL maybe. Same kind of thing happens in quantum computation. People like to write down circuits like this, for example. This is a 2-qubit circuit, where on the first qubit you perform an S gate, then an H gate, and this is a controlled Z gate, and then you do some more gates on each of the individual qubits. So a circuit like this, for example. And there's typically finite gate sets that people use that you can build in practice. So you can choose these S and H from that finite gate set. So standard gate sets, for example, that the IBM machines and the Google machines use, typically include these kinds of gates, like a T gate or an S gate or a Z gate. We can build this kind of thing from, where did it go? From the two new ingredients that we added. Sorry, these two. For example, you can build a T gate as ID plus omega. So now plus does not mean addition of natural numbers. It means direct sum of matrices. So this is a one-dimensional. This is the complex number 1. This is the complex number omega. If I put them together with a plus, that means I make a 2 by 2 matrix that has a 1 in the top left, a omega in the bottom right, and zeros elsewhere. So it's like a block diagonal matrix. In the same way, you can build S gate and the Z gate, and these three are sort of standard gates. And you can build a Hadamard gate, which is this H over here, in this way. So that's a bit of fiddling around, but you can build standard gate sets like that. And there exists proofs in the quantum computation literature that if you can build a large enough gate set like that, for example, these 4 gates, they are universal, computationally universal for quantum computing. So remember, that means if you take any unitary matrix and any error margin epsilon, you can make a circuit that approximates that unitary up to epsilon. So if epsilon gets very small, the circuit might be huge, but in principle, you can program that way with gates, quantum gate circuits, any unitary matrix. So in this kind of way, we can build this standard gate set that I've given you now with S and T and Z and H. That's sometimes called Clifford plus T, and that's known to be universal. And you can build other gate sets like, well, in our new programming language. And just like we had before, let me go back a bit. So before we had our programming language, we had a class of models, in this case, Rig groupoids, such that it's complete in the sense that any function I can actually write a program to implement it, and it's fully abstract in the sense that I can prove the two programs are equal just by equations in the model. Same kind of thing happens on this side. So we saw that we have programming language, we have a class of models. You can build, it's universal in the sense that I can make a program to implement any computation you want to give me. And the final piece of the puzzle was this full abstraction that you can, just with equations in the model, show when two programs are equal. So we saw that these models, you can represent various circuits like this, for example. You can do this in any model. So you can sort of emulate building circuits inside any model. And you can reason about that using some axioms. And these axioms are really just these 3 equations. Only 3 possible steps in any proof. Because from these axioms, you can prove things like this, that this circuit is equal to that circuit. And I think on the next slide, we'll have an example proof. And it can get quite complicated, like this circuit is equal to that circuit. You can do these things by hand. But in fact, we have a theorem saying that you can always do this. Let me explain that theorem. If you have any program F and any model, I can interpret the program in that model, and we'll use square brackets for that. And I know that unitary matrices form a model, so I can always also interpret that program as a unitary matrix, and I'll think about that with double rounded brackets. And the theorem, so the completeness theorem or the full abstraction theorem says that 2 programs are equal in the sense that they behave the same. In any model, they have the same interpretation, if and only if their unitary matrices are equal. So in some sense, I can prove in the programming, in any model, that 2 programs are equal exactly when they're equal in the sense of, actual practical quantum programming. For programs F and G from these various kinds of gate sets. It's not really important what they are. It's important to point out that the latter two gate sets are computationally universal. So these 2 gate sets you can use to build any quantum computation you like. Okay, so that's great. We have a programming language that includes reversible classical computation, added just 2 primitives and forced 3 equations. Now is computationally universal quantum programming, and we can still reason about it semantically just by equations. There's no quantifiers anywhere, and the point is you can automate this kind of thing. So you can reason about these programs in an automated way. And here's an example of that. So because we only have equations everywhere between programs, there's no difficult program transformations, it's purely equational rewriting. You can prove, for example, that this is a very simple proof. If I have a circuit, a 1-qubit circuit that first does an S-gate and then does another S-gate, is literally the same as doing a Z-gate. And I can do that syntactically. I don't have to compute the matrix for these things. I can just use the definition of S. I can use some rewriting rules. I'm not sure what happens here. I think this is a distribution rule. I can simplify some things and end up with a definition for Z. And this way, any 2 programs you can write, if they implement the same function, I can prove that they implement the same function just by a string of equations like that. And of course, computers are very good at reasoning with equations because there's finitely many programs like that, and there's finitely many programs like that, and they have like finite steps of equation, finite number of steps, and each step is a finite number of possible axioms. We can just brute force it all out or write some more intelligent theorem provers to prove that this program is equal to that program. So you can use this, for example, to say, you give me a program, I can now find a smaller program, a minimal or even optimal program that does the same thing. So you can use this to optimize things. Or you can even say things like, I want you to find the program that implements this and this function. Go find me the smallest one, please. You can outsource that to theorem provers now. So in the references I'll give you at the end, we've done this, and a substantial part of those proofs were formalized in a theorem prover called ACTA. Okay, we're coming towards the end of what I want to tell you about. So remember, the main setup was we added 2 new primitives, and they forced 3 equations. And the third equation was a bit mysterious, and in some sense, all 3 are a bit mysterious. So let me talk a bit about how you can think about these equations. So the first 2 equations were about roots, right? A square root or an 8th root. And I've sort of justified them so far by waving my hands around, I want to be able to solve polynomial equations, and this works out nicely mathematically. But physicists are not convinced by that. Okay? But luckily, there's another explanation, a justification for these first 2 axioms, which has to do with how physics actually works. Because I said the basic steps in quantum computation are unitary matrices, but you can think about them in a different way. By what's called Stone's theorem, you can think about any unitary f as an expression like this, e to the power it h, where h is some self-adjoint matrix or Hamiltonian. And this is something that physicists like because Hamiltonian sort of gives the energy value, if you like, for a certain physical system. And you just run this for a continuous amount of time t. So working with unitaries is the same as working with Hamiltonians. And in the Hamiltonian point of view, taking a square root of this unitary literally means just running that process for half the time. Because e to the power this times itself, you just add up the 2 exponents, and t over half plus t over 2 just gives you t. So we were asking for a square root of the NOT gate, for example. And a NOT gate is something that for example, photonic people can build on a tabletop with lasers and mirrors and beam splitters and things. They can implement a NOT gate. And you just do that very same process, except you run it for half the time, or you shoot the laser at half the energy levels. And that way you can implement this gate that we call V. Right? So a square root of NOT is actually physically a very useful thing. It's very easy to build. And the same thing goes for the 8th root of 1. That's also very easy to build that way. So I talked about photonics, but there's other hardware platforms where that implement quantum computers. Superconducting is one, and trapped ions are another. They both have a similar thing. So these square roots are not fanciful things. They're actually useful in practice, and sort of in that way, our mathematical model and our programming language bears out what happens in actual quantum computing in the lab. The third equation, this VSV, where did it go? VSV equal SVS, that looks a bit like this on the block sphere. That's maybe more mysterious. Oh, move that, something happened. There's another model of quantum computing, which is called anionic, which is all about you have some particles. In this case, there's 3 particles, and time is going up and down. And you move these particles around each other. So they're sort of trapped between pieces of glass or magnetic fields. And the whole computation happens by just moving them within this 2-dimensional plane. You can sort of draw their world lines. So the first particle sort of gets swapped around the second one, and then swapped around the third one, etc., and ends up in that place. And if you write out what VSV equals in that framework, you end up with this equation between 2 string diagrams. So, and this is a totally obvious thing. This is what's called the Yang-Baxter equation, and that's very fundamental in any kind of string diagrams and more generally anionic quantum computation like that. So that third equation in this hardware platform is very natural. So all 3 equations are useful, are not, they match what happens in practice. Okay, last part of the talk, we've only talked about reversible things so far. And I've been arguing that if you start with a universal model for reversible classical computing, you add some universal properties to that, you get reversible, you get a universal model for quantum reversible computing. But at the end of the day, you want to get an answer out of your quantum computer, you have to do some measurement, and that's irreversible. So that is not captured in this model yet. In the last maybe 10 minutes or so, I'm gonna tell you that you can take the thing we've built before, this programming language for quantum reversible computing, do another universal construction to it, and now you get a programming language and model that's universal for arbitrary quantum computing, including measurements. Again, first I have to talk about the classical situation, because these things are called information effects. And the idea is that you start with classical reversible computation, you add these information effects, and then you get something that's universal for irreversible, so arbitrary classical computation, where you're talking not just about permutations between sets, but functions between sets. And basically what these information effects are is the fact that you can copy and delete classical bits. So if you give me a bit B, I can just forget about it. So this is some sort of, in the programming language, you could think about this as a function erase that takes a bit that is of type that inputs a bit and outputs nothing, outputs 1. And the same kind of way you can create or copy bits that sort of create a bit out of nothing and let's say initialize it in state 0. So this is a known theorem. They're called information effects, and it's something you can add on top of your programming language to make it irreversible. So in other words, you can think about this universal property as a compiler that takes an irreversible function and compiles it into a bunch of reversible permutations together with these kinds of extra primitives. Now the idea is that we can do the exact same thing for quantum measurement. So now quantum measurement is not something that goes bit to bit, but it goes qubit to qubit. So it's a 2 by 2 matrix. And what it does is if you give me this matrix, a density matrix, it sort of zeroes out the off-diagonal things, and you get outcome 0 with probability related to A and outcome 1 with probability related to D. That's just how quantum measurement works. I'm not going to go into much more detail about this, but that's the way it works. And we're going to do this in 2 steps. We're going to do copying and deleting in 2 steps. We're going to add this, just like in the classical case, to quantum reversible computation to end up with quantum measurement. The first thing we're going to do is we're going to give the programmer the ability to allocate from a hidden heap. So I put some syntax down that says you can have all the programs you had before, but additionally, you can now have these things called lifts. where you can have a function from B1 to B2, like a new function, an irreversible function from B1 to B2, is the same as an old function from B1 to B2, but not from B1, actually from B1 plus something else, B3. So there's some heap these functions can use that the programmer cannot see. This is a universal property in the sense that you can give me any rig category. I can make a new rig category that satisfies this. And the universal property is that this object O, which was the unit for addition, so sort of like the natural number 0, has now become what's called initial. So for any other object, there's a unique map from 0 to that other object. And that's sort of like allocating a bit, or allocating a pair of bits, or a triple of bits. Right, so the first step is we allow heaps. And it's a very simple thing to add. Second thing is I'm going to allow a garbage bin. I'm going to allow you to hide part of the output. So again, sort of you have the basic types. We're going to add a new kind of type, and a new kind of type from B1 to B3 is the same as the old functions from B1 to B2. But now you're also allowed to have some extra output that we're going to ignore. Right? So this sort of gets leaked to the environment, if you like, or we're just not going to look at it. In the billiard table, there were 2 inputs and 3 outputs, if you remember, and we sort of forgot in some sense about 2 of the outputs and only care about the AND. That's the kind of thing that's happening here. So now you can write a function in the new language that takes a bit and just discards it. We can forget that it exists. It gets compiled down to something that where it still exists, but we can't touch that anymore. That's sort of out of our control. Again, this is a universal property. It has very simple syntax. And the universal property is that you give me a rig category, I can make a new one where now the unit for multiplication, the object I, that is a bit like the natural number 1, has become terminal in the sense that there's a unique map from anything to that terminal object. And these things, you can think about them as discarding or forgetting or deleting bits or triple of bits or a pair of bits. Okay, so with these 2 universal properties, I'm going to allow a hidden heap. I'm going to allow a hidden garbage bin. You can now do any irreversible quantum computation because you can write down. So just like from the simple programming language we had, and the simple classical reversible programming language, you can write the Toffoli gate. In the simple reversible quantum programming language, we can write stuff like a Hadamard gate and an S gate and a T gate. In this language that we're talking about now, we have heaps and garbage. You can write down programs like projections that sort of forget the second factor in a product, and you can actually write down a function called measure that sort of behaves like it should. And you can prove the theorem that says that this programming language that we now have is, first of all, computationally universal, not just for reversible quantum computation, but for arbitrary quantum computation, including measurements. So the model for that is not just unitary maps anymore, but what's called completely positive trace-preserving maps. I'm not going to go into detail, but that's the way it works. Okay, so we've done 3 steps. First, we had a programming language for that was sound and complete and computationally universal for reversible classical programming. Then we added 2 primitives to make it sound and complete and universal for reversible quantum programming. And now we've added 2 more primitives and made it sound and complete and universal for arbitrary quantum programming, arbitrary quantum computation. I think I'm going to skip this unless somebody asks about this, because it's more about foundations of physics. I'm going to come to the conclusion. So what I've tried to convince you of is that there exists a universal quantum programming language, and we've built it up in 3 steps. And at every step, what we made sure happened was that it's very simple syntax. It's computationally universal in the sense that any function you might want to program, you can actually program. It's equational in the sense that you can prove that two programs are equal if and only if they sort of implement the same function only by a string of equations of very simple rewrite rules and fully abstract. It's sound and complete in the sense that all these rewrite rules make sense, right? They're valid in actual computations, and they're complete in the sense that you can prove that two matrices are equal if and only if the two programs are equal. And it was quite simple things that we did. We added two generators and three relations, and then we added these copy and delete effects just by messing around with the types of the programming language. That's all I want to tell you today. I'm going to leave you with some references. If you want to read more about this, these are some of the papers that I think you might find interesting. I'm going to stop there, and I'm happy to take any questions and talk about anything. Thank you.
All right. Thank you for the wonderful talk. Does anyone has questions?
그 준서 네가 잠깐 그 번역 좀 통역을 해줄래? 그 양자 얽힘에 관해서 이렇게 좀 구체적으로 어떻게 더 표현이 되는지를 설명을 더 할 수 있는지를.
Chris, he's asking about how we can express the quantum entanglement in the language of the square root of pi.
That's a good question. So that's sort of hidden underneath the bonnet, right? Because let me go back to it. Where is it? So that's not an easy question to answer. So I was talking about this 1 plus 1 as if it's a qubit. Right, so that's one qubit. If you want to talk about entanglement, you need two qubits. So there's four things. And maybe let me go back to this sort of thing. So here, this controlled X, this is a thing that takes 2 bits and implements and outputs 2 other bits, right? And it is built using this this thing called dist and this thing called factor, which mix up the types like that. So this is 1, that's 1, and that's 2. Then this whole thing is 4. So that's the right kind of type. And sort of this is where the entanglement happens. This sort of B1, in a sense, gets smeared out over, B3 gets smeared out over B1 and B2. So yeah, it's sort of way down at the bottom level. It's not something you have to think about in some sense. Does that make sense?
설명이 좀 되셨나요?
Okay, thank you.
Then I have another question. We add 3 equations to make square root of pi language. Then is it possible to prove that it cannot be done with only 2 equations? In other words, can it be proven that at least 3 equations need to be added?
I do not know. So another way to ask the question is, are these 3 equations independent? So can you find a model that satisfies 2 of the equations, but not the 3rd?
Right.
I'm not sure that's exactly the same question, but it's close to it. I'm not sure I have examples for all 3 cases where you leave out one of 3 axioms and find a model that satisfies those 2, but not the other. I think I would be very surprised if you can do with fewer. But no, I don't know.
Okay, I see.
In some sense, I mean, 3 is a nice number and it's very small, but in some sense, it's not important what the number is. As long as it's finite, I'm happy. If it's 1,000, I would still be happy, because then you can still, write a computer program to optimize these kinds of, write a tool to optimize these kinds of programs for you and reason about them. But yeah, if you can manage with 2, that would be great. Please try.
Okay, thank you for your answer. Is there any questions?
말씀해 주신 그 내용이랑 스파이더라는 거랑 어떻게 연결되는지 간단하게 설명을 해 주실 수 있는지.
스파이더요? Can you briefly explain about the connection between the square root of pi language and ZX calculus?
I can say some things. So if I go to, hang on, here. So ZX calculus is also something that happens in monoidal categories. So we're just taking the left two columns here. So you can have string diagrams like this, where you can stack things on top of each other and put things left to right, side by side. But then ZX goes a different way. They add certain primitives and kind of dots that can copy and delete things in two different colors that we think about as, you know, the Z bases and the X, copying in the Z bases and copying in the X bases. There's also various completeness theorems for those, in the sense that any matrix of a certain type you can implement with a picture like that. And you can prove that two matrices are the same if and only if the two pictures are the same, if there's a rewrite from one to the other picture. But there's two main differences. The first is, as far as we're aware, and I think I'm up to date, these completeness theorems, they always have quantifiers in them. They need something like Euler decomposition to say, you know, these two pictures are equal. If you can find some angle to make this work. If for all this there exists something, such as blah, blah, blah. So that means you cannot fully automate it. You can have a theorem assistant, a proof assistant, but not a full theorem prover. And the second difference is that ZX calculus talks about arbitrary matrices. You can build matrices and you can build ZX pictures that are interpreted as matrices that are not unitary. So in some sense, you step outside of the world of computation. And that gives lots of problems because, so a typical thing that people like to do using ZX calculus is you start with some quantum circuit, you make a ZX diagram out of it, you simplify the ZX diagram, and then you want to get a quantum circuit back out of that. But the problem is sometimes that the simple ZX diagram that you got, you don't know if it's a quantum circuit anymore. So you have to sort of re-synthesize a quantum circuit out of it or find out if you can do that at all. So that's the second difference. In square root of pi, you don't have this problem because you can talk about computations only. You can talk about all computations and about computations only. You never leave the realm of unitary matrices. So that's two differences between square root pi and ZX. They're similar in the sense that they both use categorical semantics and they're both universal.
Okay, thank you very much. And is there any another questions? Then what's your next step to research?
Now that's interesting. I think I put some, oh no, I didn't put them. What we're working on is actually building a compiler for this square root pi so that we can, so the kind of example programs I gave you, this kind of thing, this is more like a toy example, right? It's not a real thing. So what we're building is a compiler for square root pi that you can actually build large programs and prove things about them and optimize them and try to write less toy examples in this language. So not just, you know, gate teleportation or Grover's or Shor algorithm or something like that, but some bigger quantum algorithms just to see what it looks like. And eventually, I think something like the square root of pi, I mean, if you look at the kind of programs you write this way, maybe you don't have to know about circuits anymore, but they're still quite low level. You have to think about bits and qubits. Ideally, in the further future, I would like a higher level programming language that's sort of more intuitive in some sense. So if you think about this as a program, pi, the base language as a programming language for bits and permutations, that's really something like assembly language, and you would much rather have something like Python or C or Java or whatever, right? Which is higher level. You can do things like recursion and loops and all that sort of stuff. I think about square root of pi as the same kind of thing here. It's the best we have at the minute, but it would be much nicer to find something that has something like recursion or if then else or coherent quantum control or something like that. That's easier to think about, where you can think sort of bigger things, where you don't have to think about all the details about bits and qubits anymore. That would be my ideal, but I think we're not there yet.
Thank you for your answer. If there is no more questions, then we can conclude today's seminar here. Thank you again for Chris, the wonderful talk. And thank you for attending anyone here, and have a nice day.
Thank you all. I was very happy to be here. If you have any questions, I think I put my email somewhere on the slides. I will send you the slides and please get in touch. Thank you and have a great day. Bye-bye.
Thank you very much, Chris.